Hi, I'm Matt Noyes.
I'm Joe Rice.
I'm Anthony Del Castillo.
And this is Lab 3 Polarimetry with Mueller matrices.
In this lab, we discuss Mueller matrix polarimetry. Most importantly, the two main concepts of this lab were the polarizance vector and diattenuation. Diattenuation is the property of a transmitting material in which light transmittance depends on the incident polarization state of the light. A diattenuating material will absorb linear polarization along one axis preferably. The polarizance vector tells us how our light is polarized and in what point on the Poincare sphere the polarization state of the light is. Also, it is important to talk about retardants. A retarder is an optical device that resolves light waves into two orthogonal linear polarization components and produces a phase shift in between them. Ideally, retarders do not polarize, nor do they induce an intensity change in the light beam. They simply change the polarization form.
Polarization is an important concept to learn because many optical systems' performance and functionality depend on polarization. One common optical device that depends heavily on polarization is an optical isolator. An optical isolator uses two linear polarizers and a Faraday crystal to control the direction in which light is allowed to propagate.
So in this lab, there were several key results, but there were a couple that we're going to discuss here. So here you can see our Poincare sphere and Mueller matrices for corn syrup. So for our minimum path, you can see that it's a circular retarder. This is because corn syrup is an optically active material. Therefore, the geometry of the corn syrup plays in how it polarizes light. So here you can see the maximum path for the corn syrup. The retardance has increased as expected, and it also demonstrates that the syrup has different indices for right-hand circular polarization and left circular polarization. In section B5, we examine creating circular polarizers by combining linear polarizers and quarter wave retarders. As you can see here, the linear polarizer at 45 degrees and then followed by a quarter wave retarder created circular polarization, which is what we wanted. However, when the linear polarizer was placed after the quarter wave retarder at 45 degrees, we were not able to get circular polarization. And this makes sense as you are inputting circularly polarized light into a linear polarizer.
These results are consistent with my prior knowledge of how retarders and polarizers change the linear polarization states of electromagnetic waves in order to create both linear and circularly polarized light. However, the properties of optically active materials was a surprise to me because I thought the only way you could change circularly polarized light was by retarding or diattenuating one of the two linear polarization states.
In this lab, we liked how accurate the isometrics measured the polarization vector of the light, but we also did not like how hard it was to use the isometric software.